Okay, so question number 6 here says, what is true about the graph of D? That's our original. So on our map picture, that's the blue one. Okay? At the point where the derivative graph equals 0. Okay? So, oh yeah, this is where I was like, I can't write on it because they can't see it at home. Okay, so, I know you can't see it at home, and I don't know how to fix that, but I do want to write on it anyways. All right, so I'm talking about when the red graph crosses the x-axis. That's when the derivative equals 0. I wanted to know what was happening on the blue graph, okay? And we said that that was a peak, and we decided it was specifically a extrema, that's plural for max or min. This one is a maximum, right? I think we've gotten that far. Okay. So when it says what is happening to the door's motion at this time, well, when we say it gets to the maximum, what does that mean about the door?
Stop.
Okay, it's at its
0.
So it's at its widest opening point, right? And then it stops, and then starts closing. Okay? So what's true about the door's motion? All right, you want to say that the door really stops opening and starts closing. Okay? So when I talk about like what else do I want to do? Yeah, so the door stops opening and starts closing. All right, so we're actually going to skip the whole thing about the use the solve feature. What I want to do, all right, so if I know that the 0 on the derivative graph, oh, I typed in exactly what you typed in, but I got type error. In like Y1 or Y2 or, sorry, I don't want to leave anybody behind at home. Because, whoops, I gotta turn that off, hold on. How do I do this? All right, you have to have both of those things when you type the derivative. Okay, so, but you have to have the other stuff in Y1 or it's not going to work. So you have to have both of these things typed in. Just try it one more time for me. All right. So what I want to do with my graph here is I want to refresh our memory on how to use the calculator to actually find the maximum, okay, on the blue graph.
Oh, yeah.
Okay, do y'all remember how to use the calculator to find a maximum?
Mm-hmm.
Okay, what do you press?
Isn't it second? You have to do something.
Yep,
like
second and trace, because you're going to calculate something. So second and trace, and we're going to calculate the maximum. Okay, and then a blinker shows up, right? And then it asks you at the bottom for a left bound. So that means you have to move the arrow to the left. Make sure you're on the blue graph, by the way. If not, you can use the up and down arrows and it'll jump to the other graph. All right, but you need to be on the left of where you think the maximum is. And then hit enter. Okay? Then what happens?
Then you go to the right.
Then it asks you for a guess on the right. So you go back to the right to where you're pretty sure you're on the other side of the maximum, and you hit enter. and then you take a guess somewhere in the middle. So you're going to have to go back to the left a little bit. All right? The calculator absolutely needs 3 different points to get the best approximation. Okay? So x equals 1.4426937, y equals 10614.14. Okay, what does that mean in terms of this problem?
What?
You didn't get x equals 1.44?
I went left and then to the right,
And then you have to take a guess in the middle. You have to do 3 things.
just like random.
Yeah, somewhere in the top. There you go.
Okay.
Okay.
I thought we said left and right.
1.44, but the end decimal's on the middle.
Okay, yeah, but it's close. So remember, everybody's pixels are a little bit different. And so like the newer calculators, the pixels got a little bit better. And so this is like that fancy color version or whatever. So the pixels are a little bit better, but you should still get roughly the same 2 values. Yeah? Okay. All right. What does it mean in context of this problem?
It just shows you where the maximum is at.
Okay, so what does the maximum in this problem mean?
Where the door starts. Closing. Oh,
Okay,
it's where the
so
derivative equals 0.
Okay.
Prime, whatever.
Okay,
And then,
but I'm not math. Like, I don't want to link this to the math yet. Okay? What is the 1.4426, what does that stand for in this problem? Say that again, I didn't hear you.
How far is it slash what the lines?
how long it takes to get.
Okay, so you said how far in seconds, is that what you said? No. Okay, it's time, you're right. So the x is my time. It took 1.4426937 seconds to get to its widest opening. All right, so what is the 106.14757? That's the degrees. That's the degrees of how wide it is, right? And so we can say that the maximum degree of opening, right, is 106.14757 degrees, and at time 1.4426, whatever, right? But you can round those to 3 decimal places. Okay, so just want to make sure you can interpret information from a graph into the context of the problem, because that's really what calculus is all about, right? We're going to be relating real context to graphs, and you have to be able to make that relationship and explain it in words, okay? All right, so now, let's see. Okay, and then we talked about, let's see, I want to make this bigger. Nope. Oh yeah, that was good. Okay, so let's make this a little bit bigger. And so then the other connection that we made, and again, folks at home, I'm sorry you're not going to be able to see what I'm writing, but hopefully you can catch on with me. All right, so we said, okay, so we hold on. So, we made the connection between there being, a 0 on the derivative matched up with the maximum on the original, because what was happening before we got to 0, like where on the derivative I was where in terms of above and below the x-axis? You were above, okay? So the derivative was positive. What was happening on the original graph? It was increasing. So remember us making that connection? Okay? And then when I crossed through the 0 and went below the x-axis, the derivative was negative. What was happening on the original? It was decreasing. Okay? So, like, those are absolute connections that you have to be able to make. When the derivative is positive, the original graph would be increasing. When the derivative is negative, the original would be decreasing. But you can make that connection the other way. Meaning, if you already know where the original is increasing, you also know where the derivative is positive. If you know where the original is decreasing, you know where the derivative is negative. And so wherever that changes, the increase to decrease, that's where the derivative would have to have a 0. Okay? All right, so now I want to look at the other, whoops, slide that over a little bit more. All right, I want to look at the other part to this question, which said in number 8 here, use the minimum feature of your grapher to find precisely the value at which the derivative has a minimum. Okay, so everybody, I want you to, like, at least on my screen, it's the red graph. So yours is in Y2. All right, I want you to find the minimum on that graph. Okay, so how do you find a minimum with your calculator? Second trace, number 3. Now, right now I'm on the blue graph, So how do I get to the red graph? If I press down, the down arrow, it'll jump to the other graph. Okay? But then you use the right and the left arrows to get, all right. Oh, did you notice what happened? So I didn't move it. And when I hit straight down, it jumped straight from the max to the 0. Right? That was kind of cool. Okay. All right. All right. So then we want to move right and left until we get to the minimum, but make sure you stay somewhat to the left of it when you take your first guess. And then make sure you definitely go beyond it to take your right guess. And then just come somewhere back in the middle and take your final guess. Okay? All right, so did y'all get the 2.885 and then the negative 27.067, whatever?
Yeah, you can't see the volume on these copies.
Okay, so what you want to do is you want to change your window to go a little bit further down in the y values. So you want a little bit bigger negative y value. So like maybe negative 30, I don't even know what we put in there.
Negative 50 is enough.
Negative 50 is plenty?
Yes.
Okay.
I got like 2.1185.
Did you do all 3?
Mm-hmm. Can I make it bigger?
No, you have that going down. See how yours is all jacked up right there?
Mm.
Your calculator screen is all jacked up right there.
Yeah.
All right. So it actually was a 2.8. Yes, it was. But your thing was running through. You're on the wrong graph. But you did it looks like a 2.18, but because of where your calculator's messed up, it was a 2.88. Look at the y value. If that's the same, then you definitely should have the same x value as us.
Negative
0.067.
27.5.
Yeah, so yours is 2.885. It's just because your screen has that weird thing going through it. Yeah. Okay. Sorry. All right. Are you guys at home getting the same values on your grapher? Okay. All right. So that's the minimum on the derivative. I want to know what that lines up with on the original. Okay? So again, at home, I know it's going to be really hard because you can't see the little line I'm drawing, but I'm going to put a point and then try to go straight up from there. Okay? And I want to know what kind of looks like it's happening. Okay. So it's decreasing through it, yes. Okay. What might you be able to say about the curve before it that's different than the curve after it? And this might be a new terminology.
Steeper before it.
Okay, but I'm talking about. Okay, I see what you're saying there. But I'm talking more like the curvature of it. And again, it might be a new concept.
Oh,
But-
it's something to do with the video? The secret line.
Okay, it's kind of on the part that looks kind of straight. What I'm talking about is like before I get to the place where they line up, I've got a curvature. I got a curvature that's doing this, right? But then afterwards, the curvature does this. Okay.
So it bottoms out.
All right. Well, no, it just curves a different way.
Yeah.
So you got one that's curving almost downward, right? And then almost downward. And then the other one's curving with almost like an upward, okay? So that's a terminology, a math term. When the curvature changes, that's called concavity.
Oh, yeah.
All right, the concavity changes. All right, and so, let's see. How do I want you to write this? All right, so when, all right, put it down. Okay, so I want you to write something like when, oh, they can't see that. Hold on, I gotta change my pencil. Get rid of this, get rid of this. Use my pencil here. Okay, can y'all see my handwriting now at home? I started writing the word when. Can y'all see that? Okay, so when the derivative, right, has a minimum, and actually that's any extreme also, we'll, a t,
Yeah. Oh.
when d prime of t, when the derivative of d is a function we've been working with, right? Okay, so when the derivative has a minimum, d of t, that's the original, all right, changes concavity. All right, so we're going to make this more formal. We're going to add this to our list of things that we've talked about in a minute.
So it went from going down to start curving up.
Okay, so yes, so again, because I can't write over here, yeah, they can't see that. So when I say changes concavity, here I'll just draw the graph here, all right? I'm talking about this point right here. The graph changes from curving downward before that point to upward almost after that point, okay? So that takes us right into this next piece. It says the point in problem 8 is called a point of inflection because that's a way to describe where the concavity changes, okay? A point of inflection. All right, so there are lots and lots of connections that I know that it doesn't quite seem like we've made them, but we have. All right, so what I want us to do is basically make a big old list of connections between the derivative and the original that we can talk about,
I think we
okay?
did that, unless it's different.
What?
I think we did that.
No, but there's more to it. There's more to it. So we're just going to start from the beginning. So some of these will be repeats from what we did yesterday, and we're going to add to it. Okay? All right, so I'm going to make this full screen here. All right, and I don't want to miss any. Okay, so let's talk about the ones that the connections we made yesterday. Okay, that we already reviewed today. All right, what did we say?
When f of x is negative, or f prime of x is negative, and f of x is decreasing.
All right, so when f prime of x, so these are generic, f prime means derivative, right? Okay, what's a math way to write something as negative? What's a math way to write that? What's a math way using math symbols to write that something is negative? No, like that a whole function is negative.
Oh, less than 0.
Yeah, there you go. So when the derivative is less than 0, that automatically means negative. Can you see?
Mm-hmm.
Okay. All right. What did you tell me about f? When the derivative was negative?
The regular graph is decreasing.
Is decreasing. Okay, good.
And
All right, so remember what that meant for our problem? That meant that when we got the derivative was negative, the door was closing. Okay? Right? So the degrees were decreasing. All right. And when the derivative is positive, so how can I write that in math symbols? Greater than 0. What was happening on F? It was increasing. Or in our problem, the door was opening. Okay? Well, what falls, like, which one, what if I have not really talked about if I'm just saying negative and positive? What's between negatives and positives? Okay, so when the derivative was equal to 0, what was happening on F?
They have a relative extreme and it changes.
All right, f of x, because that's important. When f prime of x equals 0, when the derivative equals 0 and changes sign, that's important. Make sure you include that. What was happening on f of x? It has a what?
Extreme, relative extreme.
A relative extrema. Extrema is plural for max or min, right? Okay, so max or min. All right, well, how do I know, how do you think you know if it's a max versus a min?
Wait, you're saying?
Like, how do you know which one it is? Okay, but what if you don't have the graph?
Looking at whether it starts off positive, I don't know.
All right, so we have a max on F. I guess we could say relative max. We have a relative max on F. All right, well, what would be happening on the actual graph of F to have a max?
Probably going up to a point and stopping.
All right, when F is increasing, then decreasing, right? You with me? A graph has to go up and then come back down to have a max. All right, well, what would be happening on the derivative?
F of x would be positive and then negative.
Okay, so f of x would have to equal 0 and change from, good, positive to negative. All right, do you see that connection? All right, so then we would have a relative min on f of x when f of x, so I know y'all already wrote this and that's okay, you don't have to edit it, but I'm going to say changes from increasing to decreasing. All right, so when f of x changes from decreasing to increasing, right? Because, I mean, when I look at the graph and it goes down and then up, I have a minimum, right?
Mm-hmm.
Okay, but then what's happening on the derivative?
The derivative is negative and positive.
All right, it equals 0, but specifically changes from negative to positive. Okay? All right. Now, we just talked about that point of inflection. Okay? What was happening on, all right, so f of x has a point of inflection when what was happening on f of prime?
It had a
It had a what?
concavity.
An extrema. Okay, when f prime of x has a relative extrema. Now, there really doesn't need to be a difference between max and min there because a flex point is a flex point. Okay? But,
Oh, the regular function.
okay, so the original function had a point of inflection when the derivative had some sort of extrema, right? A max or a min. But a point of inflection is where the graph changes concavity. Okay? So just make sure you understand that. A point of inflection by the way, you may very well hear me say flex point for short. Point of inflection is the same thing as a flex point. Y'all see the connection there? Okay. So a point of inflection is where a graph changes concavity. Concavity is just curvature. All right, well, there's two specific concavities that we're going to talk about in this course, okay? All right, so I'm going to use parabolas to describe them, but that doesn't mean the graph is always a parabola. But it kind of has this upward motion, a U motion, if it's concave up. And then it kind of has a downward motion. We would call that concave down. Okay, well now let's bring back the idea of a relative extrema on f prime. How do you have an extrema? What has to happen?
It has to change.
It has to change from increasing to decreasing or decreasing to increasing. Okay, so let me make sure I say it the way I want to say it. All right. When f prime of x has a relative minimum, right? That means the derivative changes how? Changes from...
It has a relative minimum.
Mm-hmm.
That's like positive.
No. I'm talking about still the derivative, the actual graph of the derivative. If it has a min, then that actual graph, how do I make a min? I have to decrease and then increase. Okay, so the actual derivative changes from decreasing to increasing. Okay? But I need to make sure I say this the right way because I don't want to confuse you. Okay, so f of x, all right? So remember, the minimum on the derivative is a flex point, right? On f. Okay, well, if f prime changes from decreasing to increasing, then f would have to change from concave down to concave up. And we can go back and look at our graph real quick to make sure. All right, so if I pull my graph back up, my blinker is still on my minimum on my derivative. And if I go up to my blue graph, it's concave down before and up after. Okay, so you have to be able to make the connections between the derivative and the original, and now we're going to talk about the second derivative, because you can take the derivative more than once of stuff, of functions. Okay? All right, and so what happens when f prime has a relative max?
The opposite.
The opposite, that's right. So when f prime of x has a relative maximum, right? That means the derivative itself changes from increasing to decreasing. What's happening on the original? All right, f of x would have to changes from concave up to concave down. All right, so I've covered all of that. Okay, so now we need to talk about the second derivative. All right, well, the connections.
Should I start the next ones?
What?
Are we gonna need a lot of space in these notes?
It's just I don't know. How much space do you have? Okay, you got enough space. Okay. So every connection that you can make from the first derivative back to the original, are you with me? You can also make from the second derivative back to the first derivative.
So it's kind of like an order thing.
Yeah, so like every one that's one derivative apart, you can make the same connections. Okay? All right, so here, and this is going to be a long video. Sorry, at least it's recording. All right, so now I want to talk about a little bit about the second derivative. Okay, so the second derivative just uses two prime marks, so it's called the double prime or second derivative. All right, almost looks like quotations. All right, so when the second derivative equals 0 and changes sign, all right, let's see if we can figure this one out. What happened when the first derivative equaled 0 and changed sign?
There would be
The original had a relative extreme. So if the second derivative equals 0 and changes sign, then the first derivative has a relative extreme. Do you think you could figure out whether it was a max or a min the same way with the signs? Whether they change from positive to negative or negative to positive? Yes, all those connections are the same from one to the other. Now, I want you to make another connection. What was happening on f prime? No, excuse me. What was happening on f when f prime had an extremum? We wrote it down just a minute ago. What was happening on regular f?
the point of inflection.
It was a point of inflection. So, when the second derivative equals 0, f has a flex point. Everything is connected. Everything is connected. All right, let's make another connection between the second derivative and the first derivative. All right. Okay, so we've already talked about changing sign. That means positives and negatives. All right. But what about oh yeah. So I guess it kind of goes. When you have a relative extreme of what has to happen to the graph? No, like the actual graph that has the extreme of what has to happen on it, it either changes, decreasing, increasing, or vice versa, right? Okay, so when the second derivative is positive, would the derivative, the first derivative, be increasing or decreasing? Mm-hmm. Right. So remember when we said if there's a sign change, there has to be an extreme. So a positive would go with an increasing, and a negative would go with decreasing. So I'm making the same connections I made before, but I'm going from second derivative to first derivative. Well, what did we say about the concavity of F? Okay. So this is also when F is concave up, and this is when F is concave down. So I could actually leave out the middle, and I could say when the second derivative was positive, the original is concave up. And when the second derivative is negative, the original is concave down. So the whole point behind this exploration, okay, and it was to show you that you can use information or graphs about the original, the first derivative, or the second derivative to find information about the other ones. Okay? And so those are very, very important connections that you've got to kind of get straight in your head. All right? Now, before I stop the video, I want to kind of show you what the second derivative is good for in terms of an application problem. Okay? So let me, and my physics people, this will make a good connection for you. All right? So f of x would be like your position function. Do y'all remember talking about position functions?
The last part of physics was all models.
Oh, right. Okay. All right, well, the derivative of the position function is the velocity function. Okay, so position is like a location. You're this many feet from something, okay? Well, the derivative is a rate of change. So now we're, okay? And so that's, velocity is like meters or feet per second, right? So position is like feet. Velocity, the derivative, takes that and turns it into a rate of change, feet per second. Well, the second derivative would equate to acceleration, because you'd be moving in feet per second squared. It's the rate of change of the rate of change. Okay? And so that's what, that's why we're going to discuss the second derivative a lot, because we're going to use it for application problems in terms of a position, a velocity, acceleration, all that stuff. But you've got to know how they're connected, all right, to make those jumps. Okay? Well, so yeah, so we are going to do a lot of the same things you did in physics, but it's a lot easier to get from one function to the next without having to use those crazy formulas. Okay?